Welcome back, guys. This is part 2 of Introduction to Functions for this AP Precalculus course. So in the last video, we covered a couple of topics, and in this video, we're going to continue learning about functions. So if you feel up to it, let's get to it. Now in the last video, we learned about rate of change and basically what a function is. So now we're going to dive a bit deeper into other parts of a function that you need to know for the AP Precalculus curriculum. Now, one of the first things that you need to know are zeros. What are the zeros of a polynomial? This will do wonders for you in terms of graphing a function and figuring out what the function is just from the graph as well. So a zero is basically where does the graph intersect the x-axis? The x-axis, okay? aka the x-intercepts. X-intercepts are basically where the graph intersects the x-axis. Okay, what does that mean for it to intersect the x-axis? Well, that basically means that at whatever value x is, the function itself equals 0. So f of x would equal 0 when the graph crosses the x-axis for whatever input x. So in this case, it would be -4 or -2 or 1 or 4. Okay, now one of the things we need to know is how to figure out the function just from the graph. And I know that sounds a bit difficult, like how would you know the function of this graph? Like you can do it for linear functions, but how would you do it for like this jobbled mess here, right? But don't worry, if you know the x-intercepts, your work becomes very easy. All you have to realize is that your x-intercepts, in a nutshell, are basically factors of the function, okay? That means you can break it down into x minus a and x minus a1 and x minus a2 and so on. Here the a's would represent the x-intercepts, okay? So what we would do from there is sub in. So we'd have x, and I remember I said minus. Why is it minus now? Well, you have to remember, if we have x, if a is some x-intercept, right? A is your x-intercept. And in this case, let's say a is positive. And we know that a0 equals at f of a. Okay, f of a equals 0. Then what that means is that 0 is essentially equal to x minus a. Okay, because if we add a to both sides, then we get x equals a. And a is our x-intercept. Well, at x, that would be -4, that would be -2, 1, and 4, and so on. So here we would say x plus 4. Why is it plus 4? Well, it's a negative. So if I were to work this out, then we'd have, if I do x plus 4 and we subtract 4 from both sides, then we get x equals -4, which is what we have here. And remember, x in this case equals a, because that's the input value. So going on, I can just do this again, x plus 2, x minus 1, that's not a good one, and x minus 4, okay? Because it's now negative, because if I were to put this equal to 0, then we'd add 1 to both sides to get x equals +1. Now, we're not quite done here, okay? It's one thing that we have our factors. We factored the function. But another thing we have to realize is something called multiplicity. Multiplicity, let's say we have our x-intercept, our x-axis here. If we have a function that passes through the x-axis, right? It passes through at that point and goes on, okay? If it passes the x-intercept, then it's an odd multiplicity. But if it just approaches the x-axis, kind of kisses it right there, and then goes back down, right? Like we have here with 4, then it's something called an even multiplicity. So we evaluate it at each one. So at x equals -4, because remember we're saying this equal to 0 and subtracting from both sides, is it passing through or is it just kissing it and bouncing off? It's passing through, so it'll be an odd number. Here at -2, same thing, it passes right through it. At 1, it also passes through it. But at 4, it touches and goes back down. So at x equals 4, we denote this with a 2. Now that number can depend whether it be 2, 4, 6, 8, and even the same things with all these other ones. But a good way to assure it is that the degree Okay, this is a new vocab term. The degree of the polynomial is basically the highest exponent the variable is raised to. That's how I think of it. So if I have something like an f of x equals x5 plus 4x3 plus 2x minus 6, then the degree of this polynomial would be 5, because that's the largest exponent. And a good way to check the degree, so it should just see how many turns are there in the graph, is like what I like to say. So there's 1, then it goes up, 2, 3, 4, 5. Okay, there's 5 turns. And then what you would do is you would add up the exponents of each factor. So even though there's nothing there, it's raised to the power of 1. So there's 1. Same thing here, there's nothing there, but it's still 1, so 1 plus 1 is 2. Same thing here, there's nothing there, but it's still 1, so 1 plus 1 plus 1 is 3, plus this 2 here equals 5, and that equals how many turns there are in this graph. So we know that this polynomial is a degree 5 polynomial. Another thing that you would realize is that this function is decreasing as you move towards more positive and positive x values. And this is something called end behavior. Now, this is a lot more calculus stuff that you'll learn when you come to AP Calculus, but a way to denote it is that the limit, okay? The limit as x approaches positive infinity. What does this mean? It means that as we go towards positive infinity, towards the right side, just right, no end. What does f of x approach? Well, f of x, what is the limit? What does f of x approach? Well, f of x, as it goes towards positive and more positive values of x, it goes down, right? It goes down for infinity. So it approaches negative infinity, okay? That's the end behavior of the graph. Conversely, if we say, what is the limit as x approaches negative infinity now? Well, f of x approaches positive infinity because it's going up, right? It's going up. So since these two are mismatched, right, positive with negative and negative with positive, then we know that the function is decreasing. If it were, say, constant, right, positive with positive and negative with negative, then the function would be increasing. And just a simple way to just test this out is to just draw a straight linear line that just goes down like that. And you can just see, since this has a negative slope, right, rate of change, then the function is decreasing. If it was going to the right instead, then it would have a positive slope or positive rate of change. Now, one thing to note is that the end behavior of a function is not always going to approach negative or positive infinity. There are going to be some cases where there's an asymptote, right? A value that you're always approaching, but you're never really getting to. That is what an asymptote is, and they can be horizontal or vertical. And you'll see them a lot in rational functions, in logarithms, in exponentials, and all that. So you can expect those. So don't always think that the end behavior is going to be positive or negative infinity. And so saying that, what I mean to get at is that this is the way I represent it here. It's positive, but in reality, it's negative. Okay, there's a little negative sign there because it's decreasing. Now, there is one caveat to what we've written down. Right, this is the best we can do with the information we're given on the x-intercepts. But there's also these points here, and I'm going to do that in a different color. There's also these points here. Where are these points? Right, these points are called your local or your relative maximum and minimum. Okay, these are points where, these are essentially what you call turning points, where the function turns from increasing to decreasing. Okay, in this part it's increasing, right? At this part it's decreasing. That is what you call a relative maximum or minimum. And then these two endpoints here, right, like here, and you can't really see the area, but like just down there, right, those are what you call your absolute maximum and minimum, right? They're absolute because after this there's no other turning point. Okay, but in the middle of them there are a couple of turning points. And when you get a calculus next year, you'll learn how to figure out where these relative maximum and minimums are. But for now, we cannot express that in this because, well, we just don't know what they are, right? What I mean to say is that, you know, the relative maximum could be here and the function can look like this instead. It can still have the same x-intercepts, but the relative relative maximum minimum can change. And now there's one more thing, and this might seem obvious, but it's good to know that between every x-intercept, there is going to be one relative maximum or minimum. There has to be, right? Because just think about it. Think of like you're bobbing underwater, right? You're swimming underwater, and then you come back up to the surface, right? You went down, right? You can't just come up twice in an instant. That doesn't make sense. You have to go down for you to come up again. So that's kind of the logic here. There has to be some relative maximum or minimum between these x-intercepts. Now, these turning points, right, the green ones here, these are not to be confused with the point of inflection. The point of inflection is basically where the function changes from concave up to concave down, or vice versa. Now, what does that mean, concave up, concave down? It's basically having bowl shapes, okay? And you see a bunch of bowl shapes here in the function, right? Like these curvatures, right? These curvatures here, these are concaves, okay? These curves here, like they kind of look like quadratics, kind of, if you like isolated it, kind of. But if it's going down, right, if I were to just isolate this one right here, okay, I'll do that in another color. If I were to just kind of do that, right, this is concave down, because the entire point of this is just moving down. On the other hand, right here, this point here, this is concave up, because if I were to do the same thing and like kind of model it as a quadratic function, then it just be moving up the entire time, okay? And this point here, and it's not always going to be the x-intercept where the point of inflection is. In fact, I don't know where the point of inflection is. It could not be this. It could also be this point right here. You'll figure that out once you get to calculus as well. But what I mean to say is that the point of inflection is where it changes from going down to going up, or vice versa, from going up to going down. And that's what it means to have a point of inflection where the concavity, or concavity, however you pronounce it, changes. Right here, let's talk about odd and even functions. Odd and even functions are basically where, in terms of like looking at it from a graph, it's super easy, okay? Super easy. All you have to do is look at the function, and if it's even, the function can basically fold in itself and it'll be symmetrical about the y-axis, okay? So if I were to take this quadratic function, okay, this is f of x, or I'll just say y equals x squared, okay, y equals x squared. If you were to take this and just fold it into itself, then all the points on the negative x-axis and all the points on the positive x-axis would fold on top of each other, and it would just all overlap, okay? There would be no, it'd be symmetrical, okay? It shows symmetry. Okay, something like x plus 1, right? This would just shift it up 1. It'd still be symmetrical because, again, you can just fold it along the y-axis and every single point on the negative x-axis and positive x-axis would align. But you cannot do this with this function here, right? Because if you were to do that, I'll do it in a different color. It looks something like, I guess something like that, right? If you were to do that, and that does not really look like folding it on top of each other. What this does have instead, and what makes this an odd function, is that it has rotational symmetry, which means that if you were to rotate this 180 degrees about the origin, right? So if I were to go from here to there, 180 degrees, then the new the new transform function would basically be the same thing again, okay? It'd be the same thing. If you were to shift this up and down, then it would not be the same anymore, because if this was shifted up like this, and if you, oh shoot, that's the same thing. If you were to shift it up like that, and if you rotate that about the origin, it would not map on to itself again. So what does this mean in terms of like looking at a function not graphed just in terms of x's and y's? Well, basically what it would mean is f of negative x equals f of x for an even function, right? This is an even function. And for an odd function, f of negative x equals negative f of x. So we're to sub in negative x values, and if you square that, it would still be x squared. But let's say this function right here is y equals x cubed. right? If you were to do negative x into that, it would come out as negative x cubed. Yeah, it would come out as negative x cubed. And if we add like some constant to it, then if we were to sub in a negative x to this, it would come out as y equals negative x cubed plus 1. It's still a plus 1. And that's not an odd function because according to this, everything needs to switch its sign. So this, for it to be an odd function, would technically need to be negative x cubed minus 1, not plus 1, minus 1, because we want everything to switch its signs. Here, if everything is still the same after you put a negative x into it, then it's an even function. Alright guys, thank you for watching the video. If you learned something, then make sure to leave a like, subscribe, and ask any questions you might have in the comment section. And if that's all, I'll see you next time. Bye.